What if Alice, Bob, and a million other people could all sign one Bitcoin transaction, and the result on chain looked identical to a signature from a single person? No multisig script, no extra bytes, no privacy leak. That's not a thought experiment. That's Schnorr. The magic ingredient is linearity. A Schnorr signature proves knowledge of a private key, and because every operation is linear, public keys, nonces, and partial signatures all add together cleanly. Let Alice hold private key Y and let Bob hold private key Z. Together, they want to jointly prove knowledge of X, where X equals Y plus Z. Neither party reveals their secret. They exchange only public values. The combined output is a single signature, indistinguishable from one produced by a lone signer. Step 1. Each party shares their public key. Alice publishes Y times G, and Bob publishes Z times G, where G is the generator point on the curve. Adding these together gives the aggregated public key X times G. Step 2. Each picks a fresh random nonce, a number used once. Alice picks A, Bob picks B. They share A times G and B times G, which sum to the aggregate nonce K times G. Step 3. Both parties compute the same challenge. C equals the hash of the aggregate nonce. The aggregate key and the message M identical inputs produce an identical challenge on both sides. Step 4. Each signer produces a partial scalar. Alice computes S sub A equals A plus C times Y. Bob computes S sub B equals B plus C times Z. Step 5. We sum the partials. S equals S sub A plus S sub B. Expanding, that's A plus B plus C times the quantity Y plus Z. But A plus B is just K, our combined nonce, and Y plus Z is X, our combined secret. So S equals K plus C times X. The final signature is the pair KG and S, and it verifies under the standard Schnorr equation. S times G equals KG plus C times XG. One signature, any number of signers, identical on-chain footprint. This works until it doesn't. Watch the key cancellation attack. Alice publishes her public key, Y times G, first. Bob, who is malicious, waits and watches. Then Bob declares his public key to be Z times G minus Y times G. The naive protocol simply adds the two keys together. Alice's Y times G plus Bob's Z times G minus Y times G collapses to just Z times G. Alice has been written out of her own multisig. Bob alone controls the aggregate key and Bob alone can sign. The fix is a commit then reveal step. Every party first publishes a hash of their key, and only after seeing everyone else's commitment does anyone reveal the actual key. Bob can no longer choose his key in response to Alice's, so the cancellation attack is blocked. Cancellation isn't the only hazard. Nonces are equally dangerous. If any signer reuses a nonce across sessions or picks nonces with a known relationship, the algebra leaks the private key. In a multiparty setting, one careless signer compromises everyone. The aggregate key is only as safe as the worst participant's randomness. Production protocols therefore specify exactly how nonces are generated, exchanged, and combined. The MuSig family is the standard answer. 3 variants exist, each trading rounds for guarantees. Let's compare them. MuSig-1 needs 3 rounds of communication and is straightforward to implement. MuSig-2, standardized as BIP327, cuts that to 2 rounds and can piggyback on existing key exchange, making it the current production choice. MuSig-DN uses deterministic nonces, which makes it immune to repeated session attacks. But the proof of correctness is heavy and implementations are complex. For most applications, BIP327 is the default. Now every signer so far was required. What if we only need some of them? Threshold signatures relax that requirement. A T of K scheme lets any T signers out of K produce a valid signature, even if the others are offline. The trick is verifiable secret sharing, often built on Shamir's secret sharing. Take Alice, Bob, and Carol in a 2 of 3 setup. Each splits their private key into shares, distributing pieces to the other two. Now suppose Carol is offline. Alice and Bob each hold a share of Carol's key. They combine their shares to reconstruct Carol's partial key, then run the normal multisig protocol with all 3 contributions. The signature looks identical to a 3 of 3 aggregate. 2 caveats matter. First, the chain cannot tell who actually signed. Accountability is gone. The second caveat is subtler and more dangerous, the manipulation attack. Bob runs 2 separate signing sessions in parallel. In session 1, Bob talks to Alice and claims Carol is offline. Alice and Bob reconstruct Carol's partial key together. Now Bob holds Alice's contribution and a reconstructed Carol key. In session 2, Bob talks to Carol and claims Alice is offline. Carol and Bob reconstruct Alice's partial key. Now Bob also holds Carol's contribution and a reconstructed Alice key. Across the 2 sessions, Bob has accumulated all 3 partial keys. He alone can sign anything. The mitigation requires a shared broadcast channel where every protocol message is visible to all participants, so parallel inconsistent sessions cannot exist undetected. Implementing that channel correctly, especially over an adversarial network, is genuinely hard. Step back and the picture is striking. Schnorr's linearity is one mathematical property, and it gives us scriptless multi-signatures, threshold signing, key aggregation that fits in a single signature, and privacy where multisig used to scream multisig to the entire blockchain. BIP 3.7 is shipping. Threshold schemes are active research. Lightning, Taproot, and federated custody all benefit. But every gain demands careful protocol engineering. Linearity that helps you also helps an attacker craft canceling keys. Convenience that lets one party reconstruct another's key also lets a malicious party harvest them all. The defenses are known: commit before reveal, broadcast every message, generate nonces with discipline, and use audited implementations like libsep 256K1. Aggregated signatures look like single signatures on-chain, threshold signatures hide who signed, and one bad nonce can break the whole group. The elegance is real, so is the responsibility. Schnorr's linearity is a gift that keeps unfolding, and the work of safely unfolding it isn't done.